As I mentioned, I'm worried a lot about carbon capture, sequestration, utilization, and so on, no matter what pathway is being discussed, basically because the future plans for hitting the global warming targets of 2 degrees C by 2100, especially 1.5 degrees C by 2100, all involve some form of reliance on carbon capture, utilization, and sequestration. So looking at the technical feasibility, biophysical limitations, and technological readiness limitations and so on are very critical to look at. So as I keep finding the papers, I keep adding podcasts at a very introductory level so that you can follow up the details if you're interested. So this is another review paper, in fact, that looks at the limitations of CO2 utilization and capture methods as they stand now in terms of their compatibility to the Paris agreement and the warming targets, where we need to go. So I'll have a few more podcasts and we'll keep adding as new interesting results come up. So let's start with this scope of carbon capture and utilization by looking at sources of CO2, capture of CO2, utilization, categories of CCU, what they are substituting, and how long they will put away the CCU that is put into utilization. So obviously the sources include atmospheric CO2, so you have direct air capture. There are biospheric sequestration methods considered in other podcasts that we looked at, but this study doesn't look at it, and it looks at biogenic and fossil fuels that are supplying consumption and producing source of CO2 as well, which will be point sources. So in terms of the utilization of CO2, there are categories of direct use, indirect carbonation, direct carbonation, curing of cement, thermochemical, electrochemical, and photocatalytic conversions, and transesterification, which is basically conversion of biofeedstocks, let's say through microalgae cultivation, into fossil fuels, and hydrothermal liquefaction. So under point capture from point sources, it could be an absorber or a stripper, so something that scavenges the CO2 at the source or absorbs what is being emitted. And under CCU categories, you have direct uses for, let's say, CO2 fertilization in a greenhouse as shown here, which is expected to substitute fossil fuel emissions with a CCU lifetime of days to years, depending on where it's going and how that is consumed. Because remember that utilization doesn't mean sequestration or storage, it just means temporary storage with various time scales of re-entering the system. Okay, of course some are longer time scale, for example enhanced hydrocarbon recovery, what we called before as enhanced oil recovery, pumps CO2, and the idea is to substitute fossil fuel in a way that you are putting more CO2 in than you are bringing out as oil. So this can put away CO2 for years to centuries. Indirect carbonation and direct carbonation, curing cement, involve mineral carbonates and construction materials which substitute emissions from construction and can sequester carbon for months to centuries. In fact, the carbonation of cements is considered one of the better ways by many. The conversions can produce fuels and green chemicals, so chemicals and basically reducing emissions from substituted chemicals and fossil fuel usage with timescales of months to decades. So we need to figure out the technological readiness of these in terms of where we need to be as per Paris compatible mitigation pathways. So here are the global anthropogenic CO2 emissions in gigaton CO2 per year starting in 2010, where we've been going up, and we should have already started heading down. So by 2030 we are not heading down, as I've mentioned in other podcasts. In fact, after COVID we have rebounded right back. So we by 2030 we need to be at half of the 2020 emissions. So there is the technological readiness here. I'll come to in a minute. And by 2050, to meet the 1.5 degree C target, we have to go to net zero. So Paris compatibility criteria for carbon capture and utilization, then in terms of technology maturity, which we will see the definition in the next chart, by 2030 it has to be greater than or equal to 6 by this measure metric, and emissions reductions is such that you are putting away twice as much carbon into CO2 into carbon capture and utilization as you are substituting. So the counterfactual word would be emitting as before, but CCU would reduce that by more than 50%. By 2050, TRL, technological readiness level, has to be greater than or equal to 1, but the CCU contribution emission reduction has to be less than or equal to 0, because basically we have to be taking out emissions by then, not substituting, right? So what are the technological readiness levels for CCU technologies? There are some descriptions given here by two papers that I'm not going to go into details. So looking at description by European Commission of the levels at which technological readiness is defined. If basic principles are observed, that's level 1. So methanol via photocatalytic conversion is an example. Technology concept is formulated already, so then you have ethanol and methanol via electrochemical reduction, that is an example. Experimental proof of concept exists, so that proof of concept applied laboratory research is started. Functional principles, reaction mechanisms are proven. Predicted reactions are observed, at least qualitatively. And here we have ethylene via electrochemical reduction and dimethyl ether via syngas. So that's kind of a fuel that is produced from syngas. Make sure I got DME right there. Okay. For technology readiness level 4, technology is validated in lab. So preliminary process development, concepts validated, scale-up preparation started, shortcut process models found. So there you have these examples of PCC and PMC. Sorry, I had to attend to something. So technology readiness level 4 has examples under CCU as precipitated calcium carbonate and magnesium carbonate. At level 5 you have technology validated in relevant environment, not just in the lab. So detailed process development, process models, property data, simulation of processes, and pilot plants using bench scale information have occurred. Formic examples include formic acid via electrochemical reduction in aqueous environment, sodium bicarbonate using flue gas directly. At level 6, technology demonstrated in relevant environments, so not just validated but demonstrated. So pilot trials, pilot plants constructed and operated with low rate production products approved in final application, detailed process models found. So this is the Fischer-Tropsch fuels, which are going from syngas, so carbon monoxide and hydrogen, to diesel, for example, and urea from steel gases, so combination of ammonium and CO2 captured from steel gases converting into urea. Of course, we have looked at the sequestration times of those before. At 7, system prototype demonstration in an operational environment. Examples include CO and syngas via the reverse water gas shift reaction, methane and methanol via hydrogenation of carbon dioxide. These I'm being very brief in details, but the paper is really almost 70 pages long. Review paper is an excellent source of information if you want to read it. So here, demonstration and full-scale engineering have been done, parameter and performance of pilot plants have been optimized, and so on. At 8, system complete and qualified, so commissioning products and processes integrated in organizational structures with hardware and software, and full-scale plant constructed. So these include polyols, the plastics that we looked at, construction materials from carbonated steel slag. So reducing emissions from carbon and cement and steel have always been big targets, right, as we've seen before. At 9, actual system proven in an operational environment. So this is really full-scale production on. Full-scale plant has been audited, site acceptance test, turnkey plant, production operated over full range of expected conditions in industrial scale and environment, and performance guarantees are enforceable at this point. So this is exemplified by CO2 enrichment in agricultural greenhouse gases and CO2 enhanced oil recovery. So these are shown are the descriptions of technology readiness levels and examples of CCU technologies for each level of technology readiness. So determining the greenhouse gas intensity of CCU products through substitution approach, there are equations involved. So in the system expansion via substitution approach, greenhouse gas intensity of CCU product ECCU is determined by the difference between the emissions of A and B in the system expansion via the substitution approach. A and multifunctionals. Let me read again. Sorry. Determining the greenhouse gas intensity of CCU products through the substitution approach. A and B in the system expansion via substitution approach. The GHG intensity of the CCU product E emission CCU is determined by the difference between the emissions of A, the multifunctional system, and B, the marginal production system of primary products. So you have E capture emissions at the capture process, emissions capture losses, upstream emissions coming in, primary and other products there utilized into and converted maybe back to fossil fuels and releasing emissions, or going into other energy uses where the for example transportation will release it. So CCU is basically going to displace and result in emissions elsewhere. So the difference is with the primary direct emissions, including the upstream as before, and primary and other production processes like construction, steel, and so on. So in the substitution, you're utilizing, putting away carbon for some time with various timescales, as we saw, and we are comparing that to kind of a counterfactual world where business as usual goes on, right? So Paris compatibility of CCU technologies in 2030 is looked at this way. Here we have greenhouse gas emission intensity ratio in 2030. Defined as CCU product divided by substitute product, and technology readiness level 1 to 9 again here. So we have direct use, which is not considered. Fuels, sorry, that's not shown. Fuels and chemicals, minerals, carbonates, mineral carbonates and construction materials, enhanced hydrocarbon recovery, and so on. And we are looking at atmospheric, biogenic, fossil biogenic, and fossil fuel greenhouse gas emission intensities here, as defined here. So you end up with various levels of GHG emission intensity ratios in 2030. So carbon monoxide via reverse weathering, reverse gasification system, whatever that is up here. Sodium bicarbonate is here. Carbonated slag, cementitious material is down here. Carbonated slag construction block, carbonated slag construction block for biogenic and fossil fuel are here. Enhanced oil recovery, high and low pressure, enhanced oil recovery with extra low permeability, and so various options. So this is your CO2 enriched greenhouse gas, so that's the direct use that's in here. Okay, so technology maturity of CCU technologies in terms of their 2020 technology readiness level and greenhouse gas emission intensity ratio of the CCU product in 2030 compared with its substitute. The four shapes represent the four CCU categories here: the cross, triangle, rectangle, square, and circle. And the colors are used to differentiate between the different types of CO2 sources: atmospheric, biogenic, fossil, and biogenic, and fossil fuel. For a CCU technology to be Paris compatible in 2030, it must currently have a technology readiness level of 6 or higher here, or 6 or higher, and reduce emissions by at least 50%. So this is your holy grail here compared with its substitute. Technologies in the lower right gray area fulfill these Paris compatibility criteria. The full data set is shown in the supplementary material, which I'm not going to include here. So you have urea from a fossil fuel source, CO2 enriched greenhouse gas in terms of biogenic, so that's kind of BECS, enhanced oil, water alternating gas, so EWG here is water alternating gas, and EOR with high and low pressure, EOR from fossil fuel, are both included here. Carbonated slag construction from fossil fuel or biogenic sources, and so on. But you get the idea that this phase diagram is looking at a very nice way of saying what technology readiness is needed by 2030 compared to 2020 greenhouse gas intensities, and what is being substituted and how to measure this. So here Paris compatibility of carbon capture and utilization technology in 2050 is looked at. So greenhouse gas intensity of CCU products in 2050 in kilogram CO2 equivalent divided by kilogram CO2 utilized. So again, it's what is being substituted. The four shapes represent again the four CCU categories as we looked before, and the colors are used to differentiate between different types of CO2 sources as in the last figure. The TRL is not indicated because 2020 technology maturity does not preclude technologies from fulfilling the Paris compatibility criteria by 2050. So we have gone past that, and we are assuming that everybody is above 6. Technologies in the lower gray area fulfill these Paris compatibility criteria. The full data set is again provided elsewhere. So greenhouse gas emission intensity of CCU product in 2050 in kilogram CO2 equivalent divided by kilogram CO2 utilized, and the various sources of carbon and the various methods or various approaches. So direct use of fuels and chemicals, mineral carbonates and construction materials, enhanced hydrocarbon recovery. So you can see that a lot of them are beyond where we want to be in terms of Paris compatibility. This is the bad news, right? So very few are down here. Dimethoxymethane direct. So dimethoxymethane with formaldehyde, and carbonated slag construction block. So this is where you want to be Paris compatible, but most of them are here, no matter which method it is and which source it is. So Paris compatibility of CCUs right now is not very encouraging. So let's leave it there and hope that some game changer will come along which will increase technology readiness to meet Paris goals through CCU, because right now even as the AR6 mitigation scenarios have come out, which I will put in another podcast, we are still relying on things that are not technologically ready. Okay.